am Honduras Mandy Paute.
And I am Ika Itrumata. And I am Bayhadia Etuan Kali. And I am Maymay Sultan Pauti. I am Ayla Tapis. And I am Mama Sahari. And I am Yasna K. Masukan. And I am Rahana Tika.
And I am Salahudin Ensemble.
And we are the Group 1.
Everything I say is the truth. Make her disappear just like poof. Then she's
Hi everyone and welcome. Today, we're taking a trip, a vertical trip, to explore the amazing world of atmospheric science and the layers that make up our planet's protective blanket, the atmosphere. Atmospheric science is all about understanding the air around us, its composition, movement, and how it interacts with everything else on Earth. It is a fascinating field that helps us predict weather, understand climate change, and even protect ourselves from harmful solar radiation. The atmosphere isn't just about a big blob of air. It is divided into distinct layers, each with its own unique characteristics. Let's start with the layer closest to us, the troposphere. This is where we live, breathe, and experience most of our weather. It is the thinnest layer, extending about 7 to 10 miles high. The temperature generally decreases as you go higher, which is why mountains can be so cold. The atmosphere's mass is concentrated here, along with the rain, clouds, snow, and all of the weather phenomena we are familiar with. Above the troposphere is the stratosphere, home to the ozone layer, our crucial shield against harmful ultraviolet radiation coming from the sun. In the stratosphere, temperature decreases with altitude, thanks to the absorption of UV radiation by ozone. Airplanes fly in the lower stratosphere to avoid turbulence. Next up, the mesosphere, where meteors burn up as they enter the Earth's atmosphere, creating a beautiful shooting star we sometimes see at night. The temperature in the mesosphere decreases with altitude, reaching the coldest temperature in the entire atmosphere. The thermosphere is a very hot layer. While the air is incredibly thin, it absorbs intense solar radiation, leading to extremely high temperatures.
Aurora borealis happens in the thermosphere because charged particles from the sun collide with gases like oxygen and nitrogen, releasing energy as light.
The International Space Station orbits Earth within the atmosphere. This also includes ionosphere, which is important for radio communication. Finally, we reach the exosphere, the outermost layer of the atmosphere. It gradually fades into space, with individual atoms and molecules escaping into the vacuum of space.
The layers of the atmosphere are troposphere, closest to Earth where weather occurs. Stratosphere contains the ozone layer, protecting us from UV rays. Mesosphere, the layer where meteoroids burn up. Thermosphere hosts auroras and satellites orbit here. Exosphere, the outermost layer merging into space. We live at the bottom of an ocean of air, the atmosphere. It's a seemingly endless expanse, yet it's a remarkably delicate system, crucial to life on Earth. Understanding its complexities is more than just a matter of curiosity. It's essential for our survival and future. Atmospheric science unlocks the secrets of our weather. This allows us to prepare, protect lives, and safeguard property. Beyond weather and climate, atmospheric science is vital for aviation and space exploration. Understanding atmospheric condition is essential for safe and efficient air travel. It also informs the design and operation of satellites, impacting communication, navigation, and Earth observation. From predicting tomorrow's weather to safeguard our planet's future, atmospheric science is a critical field. It's a reminder that sky isn't just the limit. It's the beginning of our understanding of a complex and vital system that sustains life on Earth. I hope this video has sparked your curiosity about atmospheric science.
Unlocking the secrets of our sky. Have you ever wondered why the sky is blue or how clouds form?
How many times you lived in pain? How many scars between your veins? Where were you when this was being real? How many times you missed the train? How many songs you never heard? Where were you when this was being real?
Atmospheric physics is the science that unlocks the secrets of our planet's atmosphere. Using physics, chemistry, and math, scientists study the complex interactions of gases, particles, and energy in the air we breathe. Their research helps us predict weather, understand climate change, and even explore other planets. Atmospheric physics is a vital field helping us understand and protect our planet for generations to come.
Feel the music. Let the music.
The ocean is a vast and powerful force constantly in motion. Its currents, like rivers within the sea, play a crucial role in shaping our planet's climate.
Lights you won't see shine. Where were you?
Ocean currents that flow north or south, like the warm Gulf Stream and the North Atlantic or the cold Peru Current of South America, act as a giant conveyor belts transferring heat from the tropics towards the poles. These currents have a profound impact in our climate.
There are forces in our oceans that impact every ecosystem on Earth, influencing the lives of countless creatures in their path. These forces are ocean currents, but only one is born in ice and ends in fire. Throughout its journey along South America's Pacific coast, incredible dramas unfold through tragedy and triumph.
The Humboldt Current, on the other hand, brings cold nutrient-rich waters to the coast of South America, supporting a thriving ecosystem.
This is the mighty Humboldt Current.
Scientists are constantly studying ocean currents to understand their role in climate change. They are using sophisticated models and observations to predict how these currents might shift and how that could affect our planet's climate in the future. The ocean's currents are a vital part of our planet's climate system. Understanding them is essential for predicting future climate change and protecting our planet's delicate balance. Thank you.
Did you know that sea breeze circulation is a localized weather phenomenon that occurs in coastal areas due to the differential heating of land and water? This temperature difference creates a pressure gradient that drives flow of air from cooler water towards the warmer land. During the day, the sun's energy warms the land much faster than water. This is because the land has a lower heat capacity than water, which means it absorbs and releases heat more quickly. The warm air over the land becomes gaseous and creating a low pressure area. Meanwhile, the cooler air from the water will become dense and sink, creating high pressure air. Pressure difference between the high very low pressure area over the water in the low pressure area of the land drives air from the ocean towards the land, creating a sea breeze. At night, the land cools faster than the water, reversing the temperature difference. This leads to the formation of land breezes, which flows from the land towards the ocean. Land breezes are generally weaker than sea breezes and less impactful on the weather pattern. The sea breeze circulation is a fascinating example of how local temperature differences can drive significant weather patterns. It plays a crucial role in shaping coastal climates, influencing temperature, cloud formation, and even thunderstorm activity. Understanding sea breezes can help us better predict and prepare for short-term weather changes in coastal areas.
Hello everyone, and now we are diving into the fascinating world of atmospheric chemistry, which is the science behind the air we breathe.
Atmosphere is a complex mixture of gases, and understanding its chemistry is crucial for comprehending climate change, air pollution, and very existence of life on Earth. Let's start with the basics. Atmospheric composition. The majority of our atmosphere is made up of nitrogen and oxygen. These are our major gases essential for life as we know it. Nitrogen is relatively inert, while oxygen is vital for respiration. But the story doesn't end there. Even though they are present in smaller amount, trace gases play a huge role. Carbon dioxide, for example, is greenhouse gas that traps heat and influences our climate. And methane is another potent greenhouse gas, even more effective at trapping heat than carbon dioxide. Lastly is the ozone. In the stratosphere protects us from harmful UV radiation, while ozone at ground level is a major air pollutant. Beyond gases, we also have aerosols, which is a tiny solid or liquid particles suspended in the air. So this can be natural like dust, sea salt, or human-made, like pollutant from vehicles and factories. Aerosols can be affected by scattering sunlight and influencing cloud formation. A critical aspect of atmospheric chemistry is the carbon cycle, which are continuous movement of carbon atoms between the atmosphere, ocean, land, and living organisms. So understanding how human activities such as burning fossil fuels are altering atmospheric carbon dioxide levels and contributing to climate change. So, atmospheric chemistry is a complex but crucial field. By studying the interaction of gases, aerosols, and the carbon cycle, we can better understand and address some of the most pressing environmental challenges facing our planet.
Process of carbon flow in the terrestrial realm. Sunlight shining on green forests with a focus on leaves. Carbon flows through the terrestrial realm in the delicate dance powered by two key processes, which is the sunlight and the respiration. Photosynthesis, developed over 3 billion years ago, is one of the Earth's most vital rules. Plants capture sunlight, split water molecules, and combine them with carbon dioxide to produce carbohydrates. These carbohydrates fuel plant growth and provide the foundation for life on Earth. Do you know that temperature plays a crucial role? As temperature rises, metabolic process including photosynthesis accelerating up to the point. Beyond that, extreme heat can inhibit enzymes and damage plants. However, warmer temperature often bring increased rainfall, boosting photosynthesis in water-limited environment and enhancing carbon uptake. On the other hand, respiration is the counterpart of photosynthesis. If photosynthesis makes the fuel, respiration burns it. This process releases carbon dioxide, water, and energy back into the environment. In fact, the photosynthesis carbohydrates combine with oxygen to release energy essential for maintenance and growth. Do photosynthesis and respiration balance each other? The answer is no. If they did, life wouldn't grow. Plants capture more carbons than they respire, storing it in biomass, which contributes
contribute to the growth of ecosystem. Together, photosynthesis and respiration create the dynamic carbon flow that powers on Earth. By understanding this process, we gain deeper insight into the balance of energy and carbon in our planet's ecosystem. So keep in mind that support sustainable practices to keep Earth's carbon cycle in harmony. So let us know about the understanding soil carbon dynamics. A large forest with falling leaves and plants. Soil carbon dynamics are an essential part of the Earth carbon cycle. Dead plants materials contribute to soil carbon in two key ways, the letter fall and the root decay. Letter fall, the visible layer of the dead leaves and branches adds carbon to the soil surface. At the same time, roots contribute organic materials underground and often unseen but equally significant process. Once in the soil, microbes consume the dead plant's material through process called respiration, releasing the carbons back into the atmosphere. This process is vital for nutrient recycling. In the Arctic, thawing permafrost is unlocking massive stores as a frozen carbon. As temperature rises, microbes begin to respire this carbon, releasing it as a greenhouse gases, a growing concern in a warming world. While most soil carbon use happen through respiration, some is transported by the water transfer. Eventually, reaching the processes through relatively small, this flow still plays a role in the carbon cycle, a balanced ecosystem with healthy soil and thriving plants. So, by the understanding soil carbon pathways, we can better appreciate the delicate balance that sustains life on Earth and the impact of climate change in this vital process. So, I will end this with the saying, protect our soil, protect our planet. Joining me to this wonderful topic, and I hope you gain a lot of knowledge. Thank you!
Hey everyone! Ever wonder what happens to all carbon dioxide in our atmosphere? A huge chunk of it ends up the ocean. Let's dive into the fascinating process of carbon flow in the oceanic realm. Our story begins with the ocean-atmosphere exchange. Carbon dioxide from the air dissolves into the surface waters of the ocean. Think of it like a soda. The carbon dioxide bubbles dissolve into the liquid. This process is influenced by factors like temperature and wind speed. Colder waters absorb more carbon dioxide than warmer waters. Carbonate chemistry of seawater. It undergoes a series of chemical reactions forming carbonic acid, bicarbonate, and carbonate ions. This complex chemistry is crucial for regulating ocean pH and the overall carbon cycle. These carbonate ions are vital for many marine organisms. Ocean atmosphere exchange is ATCL. The ocean isn't just a carbon sink. It also releases carbon dioxide back into the atmosphere. Ocean currents and upwelling bring deeper. Carbon dioxide reaches water to the surface, where the gas can be released. The balance between absorption and release is constantly shifting, influenced by climate change and other factors. The ocean's role in the carbon cycle is complex and vital. Understanding this process is key to predicting future climate change and protecting our oceans. So next time you breathe, remember the ocean's silent but powerful role in regulating our planet's carbon.
Welcome to today's exploration of our vital processes happening beneath the surface of our oceans. The marine environment is not only to home to countless organisms, but it plays a critical role in regulating carbon dioxide in our atmosphere. So, let's dive in the key processes of the marine carbon cycles, including the biological pump, downwelling, upwelling, sedimentations, and volcanic. The biological pump at the ocean surface a fascinating interactions occurs. Tiny organisms like phytoplankton, the ocean's plants use the sunlight and dissolve ACO2 to produce organisms' matters through photosynthesis. They form the foundation of the marine food chain. Why does the matter, the biologic pump, help transfer carbon from the atmosphere into the deep ocean where it can be stored for centuries? Investigating warming the greater nutrient by using marine life, suggesting that the global warming could make the biologic pump more efficient, potentially limited the CO2 and build up in the atmosphere. Downwelling a carbon sink. Next, let's journey to the polar regions where encounter downwelling. So these processes occurs when cold surface waters rich in carbon sink into the deep oceans. Cooling by the polar air and the formations of the sea is the increase the water density, causing it to plunge into the ocean's depth. Also, the upwelling, the bringing carbon back up. While downwelling stores carbon, upwelling does the opposite. It brings it back to the surface. Upwelling occurs in the regions where winds and current push surface water away, allowing deep water to rise and fill the gap. The upwelling zones, including the equators and the South America West Coast, these water are nutrient-rich, supporting a diverse marines, including ecosystems, and however, they also release stores a CO2 into the atmosphere, illustrating the dynamic storage and release in our oceans. Sedimentations. Carbon storage on the seafloor as submarine carbon sink deeper and settle on the ocean floor and become a sediment. Over time, this organic and inorganic carbon can form sedimentary rock, locking carbon away for millennia. However, only about 0.6 gigatons of carbon per year are permanently buried, much less than the 10 gigatons transfers from the surface waters. Why the disparity? Deep oceans water dissolve most calcium carbonate at the depth greater than 4 km, and microbial activity in the sediment consumes much the organic carbon, releasing CO2 back to the water. So these processes highlight how tightly linked carbon cycling and a deep ocean. Lastly is the volcanisms and metamorphisms. In geological carbon cycling, let's explore the role of earth crust over a million of years. Sedimentary rock like limestone rich in calcium carbonate are subducted into the earth mantle. They melt or undergo the metamorphisms, releasing their stored carbon as CO2. So this carbon eventually reaches the surface through volcanic eruptions at hot spring, completing a cycle that began millions of years ago. While these processes operate the geological timescales, it reminds us as a deep connection between the oceans, earth crust, and the atmosphere. Thank you for joining us today to explore these fascinating processes. The more we learn about our oceans, the better equipped we are to protect them.
In human realm, carbon and oxygen cycle are deeply interconnected through biologically, ecologically, and atmospheric processes. Carbon flow in the human realm, we have 4 processes. The first one is carbon input. Carbon input is a human and other animals consume plants and other organisms as food. Processes that produce oxygen. The first one is photosynthesis. Photosynthesis, plants, algae, and cyanobacteria absorb carbon dioxide and water from the environment. The second one is respiration. Respiration is human and animals release carbon dioxide into the atmosphere during respiration. The second one is oceanic contribution. Phytoplankton microscope organisms in the ocean contribute significantly to oxygen production through photosynthesis. The third one is decomposition. When organisms die, their organic matter is broken down by the decomposer like bacteria or fungi. The fourth one is combustion. Combustion is human activities like burning fossil fuels like coal, oil, gases, and release large amounts of carbon dioxide into the atmosphere.
Imagine a world where life's building blocks are in short supply. Nitrogen, essential for all living things and constantly cycling through our planets. This vital process sustains life as we know it. But human actions are throwing this delicate balance into chaos.
Natural nitrogen cycle. These inert molecules can be transferred into the soil through a process called nitrogen fixation. Nitrogen is fixed through the occurrences of lightning and fixation by nitrogen-fixing bacteria. This allows stable nitrogen to be converted into ammonia, which is then converted into nitrite and nitrate by nitrifying bacteria through a process known as nitrification. Nitrate is readily assimilated into plants, while a variable degree of nitrite is released into the atmosphere as nitrogen dioxide, a known greenhouse gas. Herbivores derive their nitrogen from plants, and in turn carnivores obtain their source of nitrogen from herbivores, in the form of protein from meat. Nitrogen from manure also enters the cycle, but in the form of ammonium ions that can be converted into nitrite. To complete the cycle, nitrate is converted back into nitrogen by naturally occurring denitrifying bacteria.
Nitrogen cycle is a fundamental process. Nitrogen is essential for building protein and DNA. It cycles between atmosphere, soil, and living organism. Ammonification, the breakdown of organic matter, releases nitrogen back into the environment as ammonia, which is taken by the plants for growth. But people's actions have messed up this natural balance. Burning fossil fuels and using lots of nitrogen in fertilizer have made way too much nitrogen present in nature. That result too serious and widespread. Too much nitrogen causes a big problem in both land and water environment. On land, trees get sick and there's less variety of life. In water, it leads to a massive algae growth which sucks up all the oxygens, creating a lifeless or dead zone. These algae also produce harmful substances that can hurt marine animals. Using harmless farming method, we can keep our environment clean and safe. By switching to organic fertilizer and low-cost energy method, we can prevent this high nitrogen problem. Learn more about the nitrogen cycle and how you can contribute to a healthier planet. Thank you.